Hello and welcome to CO 738 Probabilistic Methods. Today we'll be applying concentration inequalities, part 2. So what concentration inequalities will we use today? Recall the Chernoff bounds that if x is the sum of x1 up to xn, where each xi are independent 0, 1 random variables, then for every delta in 0, 1, the probability that x minus e of x absolute value is strictly greater than delta e of x is at most 2e to the negative delta squared e of x over 3. And again, the xi don't have to have the same probabilities for 0 and 1, so this is a rather nice bound. More generally, we had McDiarmid's inequality that if x is C Lipschitz, then the probability that x minus e of x absolute value is greater than lambda is at most 2 to the e minus lambda squared over 2c squared n. So this was better as it doesn't have to be a sum, it just could depend on n different independent trials, and changing each trial changes x by at most c. So this seems like the Chernoff bounds. The Chernoff bounds are actually a bit better because here in the denominator we have the number of trials. Above though, actually you'd be coming from the expectation really in the denominator. And so then if the expectation was linear in n, these are roughly equivalent. That the McDiarmids would imply Chernoffs. If it's not though, then Chernoffs is better. So actually we did a more general thing, which was combinatorial Talagrand's inequality, that if x is at least 0, so it's always non-negative, and it's C Lipschitz, as in McDiarmid's, and it's R verifiable, which recall means that if x is at least s, there's a set of RS trials verifying that x is large. Then for a sufficiently large t, the probability that x minus e of x is greater than t is 4e to the negative, at most 4e to the negative t squared over 8rc squared for ex plus t. So what does combinatorial Talagrands do? If we can add in non-negative and verifiability, then we can actually replace the n, if you think of r and c as constants, that n, the number of trials, by the expectation. So when the expectation is much smaller than the number of trials, this will be useful to actually get good concentration. And so from combinatorial Talagrands, you could somewhat derive an akin bound to the Chernoff bounds, as they would also be verifiable with the coin flips. So these are the three bounds we'll be using today. Last time we had used Azumas and martingales. Today we'll just be focusing on non-martingales, so using these functions. What's our plan for today is we will use concentration inequalities to reprove the key iterative lemma in the proof of Rödel's theorem, which was the solution of the Erdős-Hánányi conjecture, so about asymptotic designs. Again, that was the introduction of Rödel-Nibble. We're just going to be doing the Nibble part, not reproving that the Nibble succeeds. And what does that mean? Well, why are we doing this? Back then we used the second moment method, as that is what we knew, to prove this key iterative lemma, to do the concentrations. And instead of that, we're going to actually use our concentration inequalities. So we're going to use Chernoff, McDiarmid, Talagrands to show that actually these are concentrated, that the various variables we'll be looking at, their expectations, that they're concentrated around those, so at high probability we can sustain the nibble. So that is the plan. I will have to remind you again about the theorem that we were proving, the iterative lemma, and then we'll work through the proof and how you'll tackle it. So I think this is actually quite instructive to see a different way to prove that key theorem, that very beautiful theorem, and how to approach it, and what difference concentration inequalities makes and which ones to use. So back to Nibble, we recall Rödel's theorem on asymptotic designs in 1985, conjectured by Erdős and Hánányi in 1963, which was about the covering of the packing numbers, which Erdős and Hánányi shown were asymptotically equal, that in the limit they are actually 1. So if you take this and divide by the appropriate number. So what is that saying? That asymptotically we can pack in complete hypergraphs, we can do a complete, an asymptotically good packing or covering by these smaller complete hypergraphs. So that was the theorem. We actually showed that that followed from a more general theorem of Pippenger-Spencer, which was about hypergraphs. So it said if H is an R uniform hypergraph on n vertices with minimum degree at least 1, and you satisfied 3 conditions. That it's roughly regular, so for every x, but at most gamma n of them, d of x is 1 plus or minus gamma times d, and plus or minus again just means again in a range there. That 2, you had kind of bounded maximum degree, that for every vertex the degree was at most kd, and then you have small codegrees, that for every x and y, the number of edges they're both in, this codegree, degree of x, y, is strictly smaller than gamma d. So roughly regular, not too large max degree, and small codegrees gives you that H has a cover of at most 1 plus a n over r edges. So you would hope to do n over r when you're r uniform. Here we're saying we need a little bit more. And then you have to look at the conditions, so it's for every r and k and a, then there's some gamma, so there's some constraint on the small codegrees, and some d naught, for which if then n and d are large enough to actually get this. So that was this Pippenger-Spencer theorem saying when you can get covers in hypergraphs, and then we were indeed able to apply that to an appropriate hypergraph to make Rödel's theorem work. So how do we do Pippenger and Spencer? Is this Rödel Nibble? So we do a little bit of covering at a time. And so to do that, we had this key iterative lemma. That for every r and k, we introduced an epsilon and a gamma prime, so that then there existed a gamma and d naught. So if you're an R uniform hypergraph satisfying 1 to 3 of Pippenger-Spencer, we can get a good outcome. Namely, there exists a set of edges E prime, subset of E of H, such that E prime is roughly epsilon n over r times 1 plus or minus gamma prime. So it's a small amount of edges, roughly what we expect when we're going to do randomness, as you'll see. That the set of vertices remaining, V prime, which is V minus the vertices covered by the edges, is of cardinality of what you would expect, which if you did it out would be V prime being n to the E minus epsilon, 1 plus or minus gamma prime. And then for every x in V prime, but at most gamma prime V prime of them, the degree in the uncovered subgraph is d e to the minus epsilon r minus 1, 1 plus or minus gamma prime. So the idea is if we pick randomly these edges to use in our cover, but we make the activation probability small enough that the number of edges will be about what you expect, so that's what 4 is saying, and that 5 that you cover about what you expect, and those numbers end up meaning that there isn't a lot of overlap on that set. And then, importantly, 6 keeps the graph roughly regular in this sense, so that we can now repeatedly apply this key iterative lemma to finish off, and then towards the end you just finish by covering all the remaining vertices when they're small with just an edge for each. So I won't redo all of that. Instead, I just want to redo the part of this key iterative lemma that had concentrations. Right, so before we proved 4, 5, and 6 by calculating certain expectations and showing they were concentrated using the second moment method, so using Chebyshev's. Here, I'll walk you through how to do that with these better concentration inequalities. Now, why you say might we do that? Isn't this a bit redundant? Well, even if this is, say, of equivalent length, it's nice to know you can do it differently, but I would make the case that the second moment method, it's a bit mysterious. It just kind of works if it works out. You calculate these variants, these covariances, and hope they work. With these better concentration inequalities, though, in a sense, once you begin to see how to really apply them, mentally you can just say, oh yes, it is actually concentrated. And that will be concentrated well enough for our purposes, so that you almost really don't have to do the calculations. So that's the really nice part to me, is it gives you a mental process of how to go ahead and do these. So let's show that off. Remember, I'll just recall for you the proof setup. So throughout the proof, we assume that d and n are large enough when required. We had various gammas, gamma 1, gamma 2, up to like gamma 20, which were functions that go to 0 when gamma goes to 0 and d goes to infinity. And you choose gamma small enough and d0 large enough to get the gamma i's smaller than your gamma primes as required. And then we let E prime be the subset edges, where each edge is in E prime independently with probability P, which was set to be epsilon over D. And then we have to show that with positive probability, all of 4 to 6 hold for E prime, which we do by showing, say, that each has probability 0.99, so they altogether have at least 0.97 with the union bound. So that was the proof setup and plan, so I won't spend a lot of time. You can, again, review the old proof. So now let me prove the various 4, 5, and 6 for you, that they're concentration. So we won't do the expectations again, we'll just do the concentration parts. So the important part about E prime is how would you prove that it's concentrated? It's just a sum of 0, 1 indicator random variables, right? It's just these Bernoulli ones. So is this edge in? And each actually has the same probability. So the expectation of EI is actually P, the probability of being selected. So again, we put a 1 if EI is in E prime and 0 if it's not selected. And from before, we'd actually calculated an upper bound of the number of edges because there's roughly regular and a bounded max degree. So I won't do that again. We found that it was 1 plus or minus gamma 1 dn over r. And then by linear expectation, the expectation of E prime was PEH, which is 1 plus or minus gamma 1 epsilon n over r, because you times by p, which is epsilon over d. So I won't do that again. That was the expectation. And now the idea is to show it's concentrated, you can just apply Chernoff bounds. It's just the sum of these independent 0, 1 random variables. So the probability that x, if you say apply it with delta being gamma 1, that x is not equal to 1 plus or minus 2 gamma 1, the expectation of E prime, would be quite small. It would be exponential in minus gamma 1 squared, which is a constant, times the expectation over 3. And the expectation is linear in n here, so this will certainly be small, in particular smaller than 0.01 when n is large enough as desired. So 4 is extremely easy. We really don't have to do anything. It's just, it's Chernoff. It's just the sum of these 0, 1 random variables. So it will be concentrated well around its expectation. Things get a bit harder for 5. So when we actually want to calculate the number of uncovered vertices, these v prime, from before we did out some calculations that showed in expectation v prime was n to the e minus epsilon times 1 plus or minus gamma prime. So for the ones that are roughly regular, we can figure out the chance that they end up not being covered, not being selected there. And it's roughly that, and the others don't make too much difference, so we got that expectation. Where do we go from there? Well, v prime isn't the sum of these random variables that are independent, is the point. It is the sum of these different variables, but whether or not vertex or not is uncovered is not independent, because the edge could end up covering multiple vertices. But importantly, v prime is R Lipschitz. And recall, we think of R as a constant, this uniformity. So what do I mean there? That selecting an edge, choosing an edge in or out, changing that, can only change whether its R vertices are covered or not. So clearly v prime is R Lipschitz. So even though it's not the sum of independent random variables, it depends on these independent trials, and each of them changing one changes it by at most R. So now you think we're almost done, because we could apply McDiarmid's. So we'd apply McDiarmid's, where the change constant is this R, this uniformity, to find that the probability of v prime minus its expectation being greater than lambda is at most 2e to the minus lambda squared over 2r squared, and the number of trials it depends on which would be e of h. So it would be all the edges of h, which we know from the previous is 1 plus or minus gamma 1 dn over r. So you might think that we're done, that we're happy now with this 5. There is an issue though. This would work if d is something like a constant, but is useless when d is much, much larger than n, right? So the number of vertices v prime is certainly going to be at most n. Ideally, we want to concentrate it then in some linear amount, or at least some, maybe even better, square root n, but that won't quite work if d is too large. So if the number of edges is much larger. And that could actually happen in the applications, such as when applying Pippenger-Spencer to Rödel's theorem when k is greater than 2l. If you look at that auxiliary hypergraph, it turns out the degree actually could be much larger there, as we're dealing with hypergraphs. So we actually need to do a bit better to rigorously prove this, not just for constant d, but for larger d. So now we've had this issue, the number of trials, the e of h, is unfortunately, in some instances, much larger than the expectation here of v prime. So instead, we want to use Talagrands. So that's our hope. We want to use Talagrands to replace that denominator where the trials were too much with the expectation. And first point we need to know is we can know that v prime is always non-negative, so we should always check that when applying Talagrands. So at least we have that done. And we knew from above that it's, Lipschitz for when c is actually r. So the last question is v prime r naught verifiable for some small r naught? Because then we'd be in business if we're Lipschitz, non-negative, and verifiable for something like constants. And you might want to pause the video and think about that. Is this the number of uncovered vertices? Can you verify that quickly, that there's a lot of them? So I'll give you the answer. The answer is no. So why is this? If you didn't come up with no, you might want to again pause the video and think through, why is this not how it works? Well, the answer is, well, to verify that a vertex V is uncovered, so just think of one vertex. To verify that there is one uncovered vertex, I would have to show you all the degree of V incident edges are not chosen, right? I have to show you each edge. I have to show you the coin flip and say, nope, that one was, didn't come up for it. That one wasn't selected. That one wasn't selected. Do this for all degree of V, which maybe roughly D, which we just agreed on was really large. So that would, if we use Talagrands there and the change constant was on the order of D, and D was bad before, that's maybe too much there. So we can't use that. So what do? It seems like we're stuck. We tried, Chernoff doesn't apply because it's not sum of independent variables. McDiarmid's seemed good, but maybe the number of trials was too much. So we tried to turn to Talagrands, but the Lipschitz, Lipschitz was fine. The verifiability wasn't there. It's too much. So what do? Well, here's the nice trick. Here's a very useful trick when applying Talagrands is often how you do it. So you get stuck and you say, oh, we're so close, we're Lipschitz, but it's not verifiable. Well, who said you have to concentrate that variable? Why don't we concentrate a different variable? So what does this mean? Right, you have a certain variable you have in mind and you know its expectation. Sure, you have to work with that one. But when you go to the concentrations, there's no reason you have to work with that variable. Maybe pass to a related variable, which will give you somewhat a different expectation and all, but if you concentrate the different variable, it concentrates the original. And maybe that one's verified. So how does this work here? Here we'll use x to be n minus v prime, which crucially, as you'll see, has an expectation on the same order as v prime. So what is this? X is the set of covered vertices, right? So here x would be v prime's the uncovered, x would be the covered ones. And crucially, then the expectation of x is n is just a constant, is n minus e of v prime, which is n minus n to the e minus epsilon 1 plus or minus gamma prime, and we think of epsilon as some constant there, so that's indeed still on the same order of. So that's going to be important. When you want to do this trick about switching, as you'll see in a second, you really need the expectation usually to be roughly the same order. Up to some constant, but you can have one be drastically different. All right, now that I've said that, we'll talk about x. So x's are Lipschitz, right? It's the complementary variable. It's the covered to the uncovered. And so, again, changing an edge will change whether our vertices are covered or uncovered. It's the same, it's Lipschitz. The key question is it verifiable? And I claim it's one verifiable. So how does that work? Why is it verifiable? So again, you might want to pause the video and think about why the covered are actually verifiable. So then the answer is, well, for our covered vertex, you just show the chosen incident edge that covers it, right? So you just show this one edge. Maybe there's a lot of edges that are covering it, but I just need to show you one to prove that it's covered. And so that's the trick here, is that uncovered is not really verifiable. I'd have to show you that everything came up false, right? It's a longer proof there. The covered, though, is easy to see. I just show you one, and that guarantees. And so this is a very nice trick to use. So we pass to the complement, which is now one verifiable. For each covered vertex, I can just show you one edge. Maybe I'd do better because some edges double duty with covering, but I only have to show you at most one edge per vertex that's covered. And now by Talagrands, we're basically done. The probability that you're at least t away from the expectation, you get this e to the minus t squared over 8rc squared for ex plus t, so we get the e of x in the denominator, and r and c are just small constants. So c is r, the uniformity, so sorry about the doubling of r's, but that's how the setup was for Talagrands and for our Pippenger-Spencer lemma. So we get that, so r would be 1, the verifiability, and c would be r, but anyway, you just get a constant there, so we know you're concentrated definitely within the square root of the expectation, really, and certainly linear if the expectation is large, which here it will be. So this will be smaller than 0.01. So what am I saying? That tells you that x is concentrated around its expectation. But if you think about that, then with high probability, and hence so is the complementary variable, right? So if x is concentrated, they're tied together as their complementary variables, so v prime would also be highly concentrated. And that's enough. So I won't do that out in detail, but that's the trick. So to prove 5, we tried things. Mainly Talagrands ended up working. We had to pass to the complementary variable in order to verify. Then we get to the last one we'll be doing, number 6, which is actually quite hard. So how did this work from before? How do we show that most things are regular? Well, we calculated the expectation for an individual vertex, that was, say, roughly regular, as most of the vertices are roughly regular, that such vertices would have expectation about e to the minus epsilon r minus 1 times d, 1 plus or minus some gamma 12. So the ones that are roughly regular have roughly this expectation that's close to what we want, and we have to show we're concentrated. So it suffices to show that this degree, this uncovered degree, is tightly concentrated around its expectation for each vertex in V prime. So I give you a certain vertex that's actually regular there, and then we have to show it's concentrated. And how do we do that? Because then we applied Markov's and all to say that most of them are close to the expectation, and so on. How do we show that this uncovered degree, right? So what is this degree? It's the set of edges incident with V, whose endpoints end up also being uncovered, so end up in V prime. Well, there's an issue. We cannot use McDiarmid's here, right? So certainly in Chernoff's is out, it's not sum of independent things. But even more than that, we can't even use McDiarmid since we'll have the same issue. The number of trials, which is E of H, we'd have to, if all these edges are different trial, could be much larger than the expectation. So it's even worse than before, right? Because I said, well, D could be much larger than N, but vice versa. Actually, in what we're interested in, D could be a constant compared to N. And so this expectation might be viewed as more like a constant where the number of trials is growing with that. So we cannot hope to use McDiarmid's. So we have to use Talagrands. So again, we have to try to use Talagrands. The number of trials is much larger than the expectation. And the question is, can we use Talagrands? So first question, it's clearly a non-negative degree, so let's not talk about that, but is it verifiable, say R not verifiable, for some small R naught? So you might want to pause for the moment and think about, again, this question, is this verifiable? So is this uncovered degree a verifiable thing or not? So I'll tell you the answer, no, right? No. Why? So again, you might want to pause if you didn't come up with no and think about it. But it's the same answer, right? To verify an edge, E is uncovered. So I have to verify now instead of a vertex that an edge that all of its endpoints are uncovered, we have to show for all of its endpoints X in E that all degree X incident edges are not chosen. So if you thought verifying an uncovered vertex was hard, verifying that a whole edge is uncovered is even harder. So that would be too much and that would be bad. So what do we do? What do we do? So you might want to pause and think about, what do we do? How do we solve this? It's the same trick. We use the complementary variable instead. So we take X to be the degree H of V. So again, V is a fixed vertex. You look at all of its edges incident, and you take that minus the ones that end up uncovered. So really what you're counting is the vertices, the edges incident with V, where at least one of the vertices gets covered there. So at least, so the edges that get covered up by a different edge. And crucially, again, the expectation is on the same order. Because when we go to apply Talagrands, so as in 5, when you go to apply Talagrands, you get the expectation of the variable you're working with. So if we're working with a complementary variable, we need to know that its expectation is somehow roughly on the same order as the old one to get back a version that we can use. So there's a certain direction it would work, but if they're on the same order, we don't have to think about that. All right, so we've passed to the complementary variable. It's one verifiable, right? So X is one verifiable. Why is it verifiable? So again, you might want to pause and think about it. Well, for an edge to be counted by X, right? So that means one of its endpoints it's covered. So we just pick one that's covered. So we show one covered vertex V in E minus V prime. And we show that that one's covered by showing the chosen incident edge that covers it. So that's all we have to do. And this, so it's one, you just need one trial to show that an edge is overlapped by another edge. And so we're one verifiable, that's great. Now we're almost done. We just have to ask, how Lipschitz is X? So how much does changing one edge change the trial? So how much does it change X, these covered edges now? Well, you might want to again pause the video and think through. The answer is a bit harder here. So what's the answer is that changing one edge can change whether R vertices are in V prime. So that doesn't seem like a lot. You can just change whether R are covered or not. But that doesn't mean it's R Lipschitz, because what does changing a vertex do? Well, changing a vertex could change whether a lot of edges are covered. A lot of the edges incident with V. Namely, because of the codegrees, right? So it could be that all, changing whether a given vertex Y was in X could change whether V has a lot of edges in or could change all of those. But luckily, there just aren't too many edges because of the small codegree condition of condition 3 of Pippenger-Spencer. So there's at most gamma D codegree edges, and there's at most R vertices there. So in total, we can change by most R gamma D edges in X by changing one edge. So question is that enough? So by Talagrands, we get this expression where we get an e to the minus t squared over 8 times 1, which is the verifiability, times this Lipschitz constant, R gamma D squared, times 4 e of x plus t. And unfortunately, the answer is this is not enough. So if you stare at that bottom, you'll realize that this is useless since the denominator has size theta of d cubed. So we get this constant, the change constant is on the order of d, so we get a d squared, and then the expectation is also on the order of d, and then that's just not good enough, right? Because we want to show that you're highly concentrated within some linear factor, so that's just not going to work. So how do we solve this? This one you can actually do. We can use the weighted version of Talagrands that we did at the very end. So I didn't prove it, but you can derive it. So let's talk about that, is we can use this weighted version to say, well, we're somehow doing overcounting on that change constant squared, right? So how does this work in practice? Well, for a specific w in omega, so in our space, a specific outcome that has at least s, so x of w is at least s, so there's at least somehow s covered edges, we want to verify this, so we want to talk about the verifying. So I'm going to order the edges that have been covered up as E1 up to EM. And now then we set the CI to be, so we order all we order all possible edges in the space, and then we want to attribute to each edge in the possible space somehow what it wants to be responsible for. So here's how you do that. You set CI to be the number of edges E incident with V, where E is incident to EI, and E is not incident to EJ for every smaller j. So what does this mean? So I order all the possible edges, and I look at E1 and I say, okay, which ones are you covering? I'm going to declare that you're responsible for those. Then I go to E2 and I say, okay, don't worry the ones E1's covering. Which ones do you newly cover up? I'm going to say you're responsible for those. And you do this for all the possible edges. And now what have I done? I've assigned somehow responsibility. And that means that if I want to change the outcomes, then if I want to uncover these, I certainly have to uncover the one I said it was responsible. And so I'd have to get down and changing, I'd have to change those. So this might be a bit of overkill, but it simplifies how to count. Because now we satisfy weighted Talagrands with the following. We know that the sum of these CI squareds, well, each CI is at most the maximum of all the CIs. So what I'm going to do is, it's quite clever, I'm going to write it as at most the sum over I of CI times the max. The max is just a constant. I can pull out the sum of the CIs. Well, each edge only appears once, because I only say which other edge is, quote, responsible for that edge being covered. So the sum of the CIs will be precisely S, and then we'll have R gamma D, which will be, because that's the max of how many edges can I be responsible for, right? So one individual edge could only be responsible for R gamma D changes. So it's a clever trick to use this max, to use this linearity, because the problem was before that we got this constant squared, but oftentimes you can do this trick where you get actually the constant just being linear with the max. So we end up with S times R gamma D, and if you apply weighted Talagrands, then we actually get an 8 times R gamma D on the bottom there instead of R gamma D squared. So that means now we have something more like a d squared of the denominator. So if we want t to be on the order of d, then indeed this will be small. In particular, we're going to set t to be gamma prime t, and remember gamma prime is thought of as somehow being a function of, but somehow much larger than gamma. So then when we put that in, this probability, it won't be somehow exponentially small, but it will be smaller than the 0.01 that we wanted. And then that's enough to prove 6. And then we've proven that all of 4 to 6, that those things, the bad things only happen with probability 0.01, so the good things happen with 99% of the time, altogether 97%, and that concludes the proof of the key iterative lemma using Talagrands instead of the second moment method. And so what was the takeaway is hopefully you took away from this video a number of things. Try to, of course, use Chernoff if it's the sum of independent variables, great. Otherwise, this McDiarmid, this Lipschitz idea can be really good unless the number of trials is much larger than the expectation. That might mean it's not good enough. So then you try Talagrands. If the variable isn't verifiable, maybe try to write it as a sum or difference of verifiable things. So in particular, the complementary variable can be quite useful. And even then, if then Talagrands doesn't work out because maybe the change constant is too much, there's this trick about passing to weighted Talagrands, which could also be useful, of course, if it's asymmetric, but here to kind of take the square down to a linear also ends up working out. And so maybe you can appreciate that we didn't really have to do out the calculations because, we just have to be careful that the numbers balance, but we'll end up being able to choose the right t's, but more conceptually, it works. So somehow you can just conceptualize, oh, it's not this variable, it's this other variable. It's the complement one. Oh, it's verifiable. Oh, it's Lipschitz. And just trust then that Talagrands should be able to work. So I find Talagrands, this most general one, to be quite powerful. These weighted versions, all of it, the exceptional outcomes, can be quite useful. And then you don't have to do the calculations of the second moment method. Instead, you can just conceptually hope to apply Talagrands. Of course, you should do the numbers to work out, but then it works out quite well. So I hope you enjoyed our look again at Rödel's Nibble and proving the concentration with actual concentration inequalities. So that's all for today. Until next time, see you then!